Okay, so as we have our chromatography going on, right, we have our column here. I'm just going to draw it going across, and we have a stationary phase. I'm going to draw this as an open tubular column, right, where the stationary phase is all on the exterior. And we have our analyte. Let's say we've got a couple different analytes. Let's say we have analyte 1, analyte 2, and analyte 3, all in a mixture heading into the column. Now, as they all go through the column, they're going to have different levels of interaction with the stationary phase because each one has a different K that will represent that equilibrium between being in the stationary phase and being in the mobile phase. Remember that when it's in the mobile phase, it's going to be moving downward, down through the column, and we can set some kind of a detector at the end to start reading and observing when the analytes each exit the column. So if we're looking at the detector, like what kind of a signal it gets, we kind of have a 0 point in time of our point of injection. Okay, so let's do our axes here. 1 will make time, and I'll put this in minutes. Okay, and we're looking at the detector response over that length of time. So at time 0, right, we're getting our time of injection where we've injected all of these analytes directly onto the column and they start moving through the column. Okay. Now these are in some kind of a solvent, right? So at some point where we have the solvent that surrounds these, that is going to still take some time to move through the column, even if the solvent does not react at all or has no interaction, not reaction, but no interaction with your stationary phase, and so we would call this unretained. But it still takes some amount of time for that solvent to flow straight through the column. So as we're looking at what the detector is measuring, the detector is going to measure nothing, 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 until at some point we might see this unretained solvent come out. Okay, so there's my unretained solvent has hit the detector, and this happens before any of the analytes come out because, again, the analytes have interaction with the stationary phase that keep it from moving for a time, whereas the mobile or the solvent has no interaction with the stationary phase. All right, so as we continue to watch the detector, we might not have anything come out for a little while, and then all of a sudden we might see our analyte 1. Okay. Now, analyte 1 comes out first, and this would mean that analyte 1 is more likely or has a stronger affinity for the mobile phase, so it's more likely to be in the mobile phase that's moving quickly down the column, and a weaker affinity for the stationary phase, which means it will not spend as much time stopped during this time of analysis, so it comes out first. Now we might continue on for a period of time, and then let's say we see then a second peak. And this might represent analyte 2. Okay. So as analyte 2 comes out, now we know that this has a stronger affinity for the stationary phase than analyte 1, but it's still not as strong of an affinity as analyte 3, which might take a good while to come out. Maybe it comes out all the way down here. Okay. And we continue on to the detector until some end time point. This is your analyte 3. So analyte 3 has taken by far the most time to come out. So that's how we get what we call a chromatograph. A chromatogram, not a chromatograph. Okay, so this is a chromatogram. Which is our readout from the detector. A chromatograph is actually the name of the instrument. So even I sometimes mess up my terminology here, but we're reading a chromatogram. So from this chromatogram, what kind of information do we want to get? So the first thing we want to look at is what is the time for this unretained solvent? And so we call this TM, or the time of the mobile phase. Mobile phase or unretained solvent to exit the column. Okay. And this TM is simply the time it takes to go from time 0 where we injected to the time of elution for that unretained solvent. There's your TM. The next thing that we might look at here is the time it takes for each of the analytes to elute. Okay, and we call that TR. Time for the analyte to elute. Now, each one of our analytes has a different TR, so a time in order to make it elute. So for our first analyte, we have a certain time. I'm going to call that TR1. Okay, but analyte 3 has a different TR, so I'm going to call that TR3. Okay, just to denote between our analytes. But they're both considered retention times, or the time for the analyte to elute. Okay. Retention time. But sometimes if we have a really long column or a lot of tubing that goes between our column and our detector, this amount of time for the unretained solid or solvent can vary, right? If you've got a long piece of tubing, it's going to take it a long time to make it out. And so you just have a longer kind of dead time here where nothing's going to come out because even our unretained species haven't made it out yet. So it can be really helpful when we're comparing between one analysis and another, when we might have a change of tubing, in order to not look at specifically the retention time, but to look at what we call the adjusted retention time, or TR prime. This is the adjusted retention time. And what this basically says is how much time does it take for the analyte to elute after the unretained solvent elutes. Okay, so for TR prime for analyte 1, we're just looking at the difference between our TR and our TM. Okay, so TR prime is equal to TR minus TM. So that's what we're looking at there. So we have an adjusted retention time for each of the analytes. So this is our adjusted retention time for number 1, and we can do the same kind of idea here with getting the adjusted retention time for analyte 3. And we put that little prime symbol, little apostrophe, to show this is adjusted retention time, not regular retention time. Okay, so that's great. We can give you the time it takes to elute from the column. We can compare those times, but sometimes we want to compare one analyte to another. And there's a few ways in which we do that, a few different kinds of values that we calculate to show a comparison between one analyte and another. The first one of these is retention factor. And the retention factor, which we're going to use a lowercase k for, is just a ratio between the time the analyte spends in the stationary phase versus the time that it spends in the mobile phase. So again, we're even going even further from just thinking about retention time for a single analyte to taking out some of our varying factors from how long it might have spent in the column due to tubing and other kinds of factors in your instrument. And so what we use for this is TR minus TM, that's our retention time, minus that unretained solvent relative to the unretained solvent. And we can see TR minus TM is the same as our adjusted retention time over TM. So we can get a retention factor for each individual analyte. So we would have a K1, a K2, and a K3 here. But we can compare those retention factors to say something about which analyte is more strongly retained and what does that ratio look like? What extent is that difference between two analytes? And so we'll do relative retention. This is also sometimes called a separation factor or a selectivity factor. I've seen it written in all three ways. They all mean the same thing. Okay. But so what does this relative retention mean? Okay, so this is the symbol alpha. So it's a Greek letter alpha. And the relative retention is the ratio between the adjusted retention times for two analytes. So I should do this with the purple for TR prime 2 over TR prime 1. Okay. We could also write this in terms of the retention factors. So you could write this with K2 over K1. Now, we always write the relative retention as the later analyte divided by the earlier analyte, which means that this always is greater than 1. So if you've calculated a relative retention that is less than 1, then you know you just need to flip your sign. Okay? So that's it for this video. In the group work, what you're going to do is take the same kind of example and a lot of these different factors and practice calculating out your TM, your retention time, your adjusted retention time, retention factor, and relative retention. So take a stop over to the group work, and you'll be able to kind of work through this example with all of those values.